Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies. In partnership with 50+ UN, sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, I'm just trying to turn on my camera. Sorry. It's kind of slow. Okay, hang on, great. Okay, thank you. Hello, everyone, and thank you for joining us from around the world, and welcome to today's session on mapping connectivity for saving lives, which is an introduction to the early warning connectivity map that is hosted by the ITU, the International Telecommunication Union's Development Bureau, and today's event is part of the AI for Good Discovery series. My name is Vanessa Gray, and I'm the head of the Climate Change and Emergency Telecommunications Division at the Telecommunication Development Bureau at ITU, and I will be moderating today's session. So first of all, our objective is to really introduce you to our mapping tool, the Early Warning Connectivity Map, EWCM, and to demonstrate how it is used by countries in terms of delivering better early warning systems, but also a bit about how the EWCM is built, how it works, and what kind of data is behind this tool. The EWCM is an AI-powered geospatial tool that's developed by ITU in partnership with Microsoft AI for Good Lab, Planet Labs, and the Institute of Health Metrics and Evaluation at the University of Washington. So in a nutshell, what the EWCM does is combine three types of data sets that we see here to show us where people are covered by connectivity and where they can be reached by early warnings sent over digital networks. And the data sets we use are, first of all, ITU connectivity data, then second, population data to see where people are within connectivity. And then we add a risk layer to show areas that are at high or low risk of disasters, and which in the end then really allows us to identify what we call cold spots, so areas that are at high risk of disasters without connectivity and where people cannot be reached. And so as an introduction, let us first of all look at this short video, which highlights what we can do with these data sets. Thank you. Hoping this is going to work.
When disasters hit, even a little extra time can save lives. Early warning systems are crucial, especially with climate change.
Sorry, Paul, I can't see the video. Can others see the video? I cannot see the video.
I can.
Oh, black screen for me.
Yeah, it's just a black screen.
Black screen for me too.
Okay.
When disasters hit,
Do you want to use the backup, the YouTube?
When disasters hit,
Working.
even a little extra time can save lives. Early warning systems are crucial, especially with climate change increasing extreme weather events. The United Nations Early Warnings for All was established to ensure that every person in the world is protected by an early warning system. ITU leads Pillar 3 on warning dissemination and communication to ensure that every person at risk can be warned on time to take action. With 95% of the world's population covered by mobile networks and almost 80% owning a mobile phone, warnings via cell broadcast are immediate and targeted, alerting people with a distinctive siren sound. 20 years ago, over 230,000 lives were lost to a tsunami in Southeast Asia without any warning systems in place. Since then, global early warning systems have improved, but their success depends on reaching people in harm's way. And this depends on the availability of communication channels and networks. As, whatever the technology, if the message doesn't get through, it's ineffective. A key tool to understand digital connectivity is the global map of the unconnected. Developed in partnership with the Microsoft AI for Good Lab, Planet, and the University of Washington, the tool uses AI to analyze satellite imagery, generate high-resolution population density maps, and visualize connectivity data based on the ITU Disaster Connectivity Map. This initiative is one of the outcomes of the Artificial Intelligence AI subgroup for the EW for All initiative, established to cultivate public-private partnerships to leverage AI in early warning systems globally. This tool visualizes how many people live in places beyond the reach of fixed broadband and mobile networks. It helps us identify population groups vulnerable to natural hazards, as they cannot receive digital emergency notifications. Knowing where people are and how they can be reached is essential. In places like Vanuatu, the tool has harnessed the power of AI, satellite imagery, population data, and ITU connectivity data to identify communities that are unconnected. This information helps governments, companies, and international organizations adapt early warning systems and prioritize infrastructure investments to ensure that everyone can be reached during a crisis. Today, digital growth presents new opportunities, but more must be done to connect the unconnected. With public-private partnerships and innovation, we can make sure early warnings reach the most vulnerable, offering protection and support in times of crisis. For more information, please visit www.itu.int.
Okay, great. So I think it's really important this video shows not just how the early warning connectivity map works, but really also how it is linked to our work on early warnings for all, because for countries to be able to reach people, they need to know the people that can be reached via digital networks, and this is really how we're using this map. So today we're joined here by an excellent panel of speakers who bring with them technical research and country-level perspectives. First, Cheryl Maureen Sherman, who is the focal point for telecom and ICT data at the Liberia Telecommunications Authority. We also have with us Paul Hamilton from the ITU, from our Climate Change and Emergency Telecommunications Division, and also Caleb Robinson, who's the principal research scientist at the Microsoft AI for Goods Labs. And thank you all of you for being with us today. And We'll have about 10 minutes for questions and answers at the end of this of their presentation. So please already now feel free to submit your questions or during the presentations, and then we can get back to those at the end of the event. So our first presentation is about the use case. And we will be demonstrating how Liberia is already using the EWCM, how it is helping Liberia to make better decisions in terms of early warning systems, but also in other areas before we then get into more the technical details on how the early warning connectivity map is built and the data behind it. So with this, Cheryl, I would like to hand the floor to you. Thank you.
Thank you, Vanessa. Hi, everyone. Just want to say thank you to the ITU Early Warning Call and to everyone that has joined this webinar. I'm just going to briefly talk about our experience using the system and what it has done for us. Can you move to the next slide, please? Next slide, please. Thank you. So I'll give you a background. We, as a country, we're just in the beginning stages of the work. Can you go back to the first slide for me, please, before the spillover? Yes, just there, so I can give a background. So we're still at the initial stage of the project, of the early warning project, and we're already seeing the benefits it's going to bring before we even complete the project. That's the amazing tool of this system. Last year, we had the ITU, one of the ITU team come over in December to give stakeholders involved in disaster management some training in the CAP alert, and also to brief us on what we need to do as a country. So basically, our next step now is the National Emergency Telecom Plan and some stakeholder governance and mapping that needs to be done. One of the key things that was also done previously to that was the development of the connectivity map, which has yielded so much benefits for us. And the information that we gathered showed where people can't receive early warning messages and the people that are exposed to medium to high floods. That was very beneficial data for us, not just me in the data section, but also those in the policy section that is handling the overall early warning for all projects. Next slide, please. So I want to give an example of how the data looks like. This is one of the counties in my country, Liberia. We have 15 counties, and this county is called Popolu. You see where you have all the blue areas, those are what Vanessa talked about, the coldspots. The counties where people are beyond the reach of cellular networks. So even if you were to send out a cell broadcast, they will not receive it. So the data shows you what is actually happening in these various districts in Buffalo. And the beautiful thing about the system is that it breaks down into technology as well, not just giving you population coverage offline, but the technology that exists in that area from 2G to broadband as well. So what is required is perhaps to ensure that you're on the right track is to do a verification exercise. So this was one of the slides that was done to be given to those who are in need of it. Next slide, please. So I'm going to speak about the spillover. We know what the system was set up to do, basically disaster risk reduction. But there's a spillover, like I'm saying, it's giving us so many other different things. The map, for instance, has been very beneficial to my colleagues in the Universal Access department with respect to their strategies that they need to carry out for most people who are beyond coverage to receive that coverage. We know that many of those people are people in non-economically viable areas, sparsely populated areas, hard to reach areas. And I think at some point, Paul will speak to that, to the hard to reach areas where because of floods, The team was on the ground, they couldn't go there. So basically, the data was shared with the Universal Access Fund. What the system showed us was that 73 districts were lacking coverage. And so we had to share that data to the Universal Access folks. And because of that, their planned activities to be on the ground, to do the ground truth assessment. Recently in December, we did a work in Sino trying to verify what the system was showing us to what is actually happening on the ground. And Paul is going to speak to that later on what happened in Sino. Another thing that the system has helped us with is the ICT infrastructure planning. Now, the tool is such that it shows you lack of coverage, but what is helped us to understand is that some of the issues may not be related to coverage. They could be related to poor electricity and poor quality of service, and not necessarily coverage. I give you an example. There was a senator, a lawmaker from a particular county, who kept saying that there's a district in his county that doesn't have.
I think I just lost Cheryl.
You lost me?
Cheryl, yeah, sorry, we just lost you for a moment there.
Can you hear me now?
Probably 10 seconds. Yeah, you're good. Yeah, thanks.
Can you hear me?
Yeah, we can hear you now.
Okay. All right. I was talking about the lawmaker issue. That's where I stopped, right?
Yeah.
Yes, I'm sorry, everyone. So he was making these claims that he didn't have coverage in his district. But when I worked with Paul to pull the map from that county, we realized the issue was not coverage. The issue was electricity. So we printed out the maps because.
Sorry, we lost you again. Cheryl, maybe do you want to turn off your video just
yes,
to
let me turn
save
my
some
video
bandwidth?
off.
Yeah.
Yes, please. Let me turn my video.
Can
everyone hear me loud and clear?
Yeah, now we can hear you. Thanks.
Great. So when we looked at the map from that county, we realized the issue was not coverage. So we printed a map and it was given to him, and he came back to say that indeed the issue wasn't coverage, it was electricity. Because once they have electricity issue in that county, there's only so much time that the operators, the cell tower can stay on. So that issue was resolved because of the early warning for all system. If we hadn't had that system in place, we wouldn't have known exactly what was going on there, and we would have had lawmakers accusing us of things that were beyond our control. So that's one of the great benefits of the system as well. Can you go to the next slide, please? All right. One of the impactors or spillover effect is the coordination. Not just within my institution, the coordination has improved with respect to sharing data within and without. For external data, we were able to give the data from the connectivity system to Giga, because we're in that Giga program as well. And so it saved us a lot of time. And then internally, there has been improvement in the coordination between those in the engineering department, my office data, and the universal access people. And there's so much expectation that as Liberia pushes forward in the One for All projects, where we then have coordination between all of the other agencies involved in this disaster management, we're going to have so much benefits, and we cannot wait to see that happen. And that's why my colleagues are working to see that we do the National Emergency Telecom Plan and all of the coordination that needs to be involved in including the capacity building that comes along with it. Now, this is just a fun fact that I added. You know, sometimes when you are used to certain things, many of you listening to me right now, and you have all of these system in place, you are used to them. So you sort of like take it for granted. But I come from a least developed country, and I come from a department where we barely get funding. So when we finished the map with the early warning team, whose focus point was Paul, I mean, it was amazing to actually see the visuals, the pictorial. It changed everything, not just for myself, but for my bosses to actually see how the map looked like, where the cold spots are, where we have coverage. Because what we had was simply numbers, and numbers can do the trick. There's something about the pictorials, there's something about visual, and that's what the early warning was able to do for us. I know it sounds very, very like nothing, but it meant a lot to us to see the visuals. And I really cannot wait to see what will happen. Like I said, going forward when we push forward with the projects. Thank you so much, and once again, thank you to the early warning team for the assistance they've given us along the way. Thank you.
Thanks very much, Cheryl. What I can do now is I'll give you one quick slide in terms of background of the EW for All initiative, what it's all about, and then an overview of the methods that we're using to produce the early warning connectivity map. So back in March 2022, the UN set a target to ensure that everyone on Earth should be protected by early warning systems by 2027, by next year. To reach this goal and to effectively protect people, we need to make sure that all areas of the 4 pillars of the early warning system work. These are first, risk knowledge, led by UNDRR. Second, monitoring, analysis and forecasting, led by the WMO. Third, warning dissemination and communication, led by ITU. And fourth, preparedness and response capabilities, led by the IFRC. So the ITU is working to ensure that early warnings reach the people at risk by identifying connectivity gaps, hazards, and vulnerable populations. So looking at the connectivity gaps, I really like this slide from the ITU Facts and Figures booklet, which shows us that 97.9% of the world's population is covered by a mobile cellular network. In addition, the 95.6% is within reach of a 3G plus or mobile data enabled network. So the amount of mobile coverage is increasing every year as networks are expanded gradually around the world. However, that still leaves 2.1% or 173 million people that are beyond the reach of even a 2G mobile network, and 4.4% or 362 million people which are beyond the reach of 3G plus network. This is really important, okay, because this is a lot of people. If we were to add up all of the total populations of France, Germany, Austria, and Switzerland, that comes to less than 173 million people. If we're going to consider the number of people beyond the reach of 3G plus network, you would also have to add the total populations of Italy, Spain, Portugal, Ireland, the UK, Belgium, and Luxembourg. So this is still quite a large connectivity gap left. So geography really matters. Understanding where people can and can't be reached on a mobile network is essential for effective disaster response. As Cheryl was saying, the national reported coverage statistics can tell us that 97.9% of the world's population is within reach of a 2G coverage and can therefore receive early warnings sent by SMS and cell broadcast. But where exactly are the other 173 million people who can't receive them? So to address this gap, this is what we've developed in the early warning connectivity map, where we compare population, coverage and hazard data sets to identify these, to pinpoint these connectivity cold spots where people can't receive early warning messages. So far, we've calculated these indicators for 50 countries, and we're continuing to scale that this year. So how do we do this? We're overlaying 3 types of geospatial data. The first is population density, and we're fortunate to be able to work with Caleb and his colleagues at the Microsoft AI for Good Lab, with Planet Labs and IHME at the University of Washington, who are using AI to generate high-resolution, time-enabled population density datasets from satellite imagery. Caleb will talk about that more in the next section. Secondly, we're able to update historic coverage, cellular coverage maps using new coverage and connectivity data sets, which can reveal to us previously undocumented coverage. In the case of Liberia, working with the regulator LTA and the mobile operators who provided for us the cell site data, the coordinates of cell sites in Liberia, we were able to compute a high-resolution cellular coverage map that has been developed by Mass Analytics and CloudRF for the GSMA. And then we augment that with connectivity data. So this is data that's been received from end-user devices and collected on at least three different platforms, from Speed Checker, Facebook and Meta, and through Ookla. And when we overlay these 2 types of data, this can show us which, at 100 square meter grid granularity, this can show us which population is within reach and beyond the reach of networks. So here's just a quick example that I found for Liberia. So the blue cells of population beyond the reach of cellular coverage, and I'm looking here at 2 settlements on the coast, so possibly exposed to the risk of coastal flooding, and on the mouth of a river, so definitely exposed to a high risk of the river flooding. And these settlements were beyond the reach of a cellular signal, apart from this one cell here, which is colored in yellow. And the third part is we overlay the hazard data. So as a baseline data set, we're using the World Bank's Think Hazard data set, which categorizes 11 different natural hazards into 4 different categories: high, medium, low, and very low. This data is available at Admin 1 or county level. And if we zoom in, it's also available at Admin 2 or district level. And we can see here at a better level of detail which districts are exposed to which natural hazards, ranging from no risk through to very high risk. This is the map for coastal flooding risk. And this is the map for urban flooding risk. So I'll stop at this point and hand you across to Caleb, who can talk more about the work that they're doing on population density mapping. Thanks. Caleb, over to you.
Sure, thanks, Paul. Yeah, just next slide. So our team is working on the building density and height component that feeds into the kind of global population maps that we're using for this project. And we really start with PlanetScope quarterly satellite imagery layers. These give us a consistent image of the world for a given 3-month time period. For example, this slide shows the state of the world in the second quarter of 2020. And the imagery is at a 4.7 meter per pixel resolution, which comes out to around 7 trillion pixels over land per quarter of imagery. And I think Paul advanced to the next slide. This shows the state of the world 5 years later in the second quarter of last year. And next slide. From the imagery, there are really two main steps to create a population layer. The first step is the part that we work on that I mentioned. We generate these gridded building products from satellite imagery using AI models. And the second step is done by our partners at the Institute for Health Metrics and Evaluation at UW, which involves combining the building density and height layers with high-resolution population projections that they develop and other gridded covariates, where they estimate the number of people that live in each 100 by 100 meter patch of land on the planet. So I'm going to zoom in on the building density component over the next couple of minutes, because that's where we use actually AI methods here. Next slide, Paul. So to start with the model training component, we use a convolutional neural network, more specifically a UNet architecture with a efficient net backbone that has two prediction heads. One is for the building density estimation task, and one is for the building height estimation task. The model takes as input the PlanetScope or a PlanetScope image and a building density prior that we generate from Overture Maps building footprints. That gives us a strong idea of where buildings are, but during training, we augment the model so it doesn't completely rely on that layer. We stack both of those channel-wise, and then the model, like I said, directly regresses the two target values for every 8x8 group of pixels. So final output resolution is around 40 meters by 40 meters. Just some details on training. We use Overture Maps, Google Open Buildings 2.5D, and Microsoft Building Footprints as weak labels to train the model using a Hubert loss function with hard sigmoid activation. During training, like I mentioned, we randomly zero out the Overture Maps prior so the model doesn't become fully reliant on it. And we found that training data selection is really a key part of training. We experiment over different weighting strategies for sampling areas to train on, and we find that sampling inversely proportional to building density, for example, doesn't result in a good model. You miss out on a lot of empty areas of the world that you need to show the model so it doesn't create false positives. And you actually have to tune that weighting scheme pretty carefully to get something that works. Similarly, we found that building mini batches to show to the model during training need to include imagery across both different years and different seasons of the year, even though the labels that we have are pretty much static in time. Final point here is that we found training for a long time with cosine learning rate cycles is really effective, and really the longer that we let the model train, the better our final performance is. Next slide, Paul. I think equally important to developing an AI model using all the techniques that I just mentioned is how to run inference with that model over a huge amount of imagery. Once we have the model, we need to run it over the entire world for 5 years of quarterly imagery. And in total, that's almost a petabyte of data. So we do this with 130 GPU nodes on Azure and parallelize inference over all of those across all the imagery. And some important points here is that really minimizing the latency between where the imagery lives in cloud storage and the model is the key variable for making this process feasible. You want to have the imagery coming into the model as quickly as possible and the outputs from the model being written back into cloud storage as quickly as possible. And all of the tuning that we've done, more details are in our paper, make this fast. So next slide. So just an example now of what this looks like. This is imagery from Q2 2020 in Lusaka in Zambia, which is the capital city, which is growing at a very, very fast rate. So if you advance one more, I think the rate of growth is around 4.5% year over year, and that's been happening for years, so really exponential growth. And if you go to the next slide, you can see what the imagery looks like in 5 years later between kind of 2020 Q2 and 2025 Q2. Yeah, and then maybe flipping back and forth, we'll let people see what's changed here. And then advance the next slide. This is what the building density product looks like for the first layer, so 2020 Q2. And once we have now the quarterly building density and height predictions per quarter, you can advance to the next slide. We can compute the change in volume per pixel. And here the green areas show places in 2025 that have a significantly larger building volume growth in subsequent quarters. And for places that are growing so quickly, like in Lusaka, knowing where these new buildings are and therefore where people are going to be living is really critical for understanding now populations that might be out of coverage. And that's why having kind of up-to-date building density and therefore population products that go into this early warning for all system is really, really key. And then I think I can hand it back over to Paul. I think I just have one final slide that says, if you want to find more information about the building part of this work, you can go to the open source repo at github/Microsoft/buildings. So over to you, Paul.
Okay, thanks, Caleb. I've just got a couple more slides to finish this the main presentation. And what I'm going to do is just walk you through the outputs from the EWCM for Liberia. So this is the population density coverage map for at a 100-meter resolution. We scaled it up from 40 meters to 100 meters to intersect with the other data sets that we've got. These green blobs show the fixed broadband data points that we collected using Speed Checker and from Ookla. This is the 2G cellular coverage computed from the cell tower data from mobile operators, the 3G coverage, and 4G coverage maps. Then when we put all of these networks together, this is a combined fixed broadband 2G and 3G plus cellular coverage map. We come to a total coverage of like 99% for Liberia, which was an interesting number. Then what that leaves is if we now show the population which is beyond the reach of these networks, which is the 1% that's left, this is about 56,000 people. Now, to circle back to what Sherelle was saying, is what we want to do next is to test and to verify that this number is accurate, that these cold spots that we've identified actually have no coverage. And the way that we do that is we've been working with our partners at Speed Checker, who developed a customized app for us. And you can download this app for free, either by going to the DCM website here, dcm.it.int, go to the About tab and click this button here, Speed Checker button, or you can go to this longer URL and download it directly from there. You just need to enable the GPS with the application and to allow the privacy settings to allow to share data, and then the results that you run on your speed test on your Android phone will be sent directly into the ITU data pipeline and into the database, and they will appear on the in the map. Two more slides. back in December. So the LTA were looking to run a pilot of a mobile coverage field test using this speed checker Android app in Sino County for a week. As that was happening, we were in touch with Alfred Toomey, who was on the ground, part of a team doing these tests, and we were seeing the results coming back into the database within an hour. A couple of findings just to point out was that we saw download speeds of up to 7 megabits per second in some towns, but in other towns there was actually only a little coverage when you're on the road, but when you were off the road or indoors, the signal was lost as a result of poor service. And in other towns, there was absolutely no coverage at all. And just my final slide is to say that actually considering the purpose of the early warning map to overlay population connectivity data and hazard data, natural hazard data. What actually happened during December was they were met with some pretty bad weather, and that this half of the country was experiencing heavy downpours of rainfall, which was causing small. These are some comments from Alfred that he sent through that were causing problems for small vehicles, and that due to the heavy rains and river floods, most of the areas that had been identified were not accessible. In fact, the only road that leads to some of the towns and villages was cut, and the only available means to get through was by fishing boat, which was not regarded as a safe thing to be doing. And even on the road on the way back to Monrovia, he said there were lots of heavy duty trucks got stuck in the mud, and there was no detour to use. So this field test, it'd be good to run this again in other parts of the country, let's say. And anyone can, if I just come back a couple of slides, just show this again. This is, as I said, it's free to use. So it's a free application. There are some data roaming charges. Sorry, it's some data usage charges. So you wouldn't want to use it on an international data roaming subscription. But so that'll wrap up our presentations for Liberia. And I'll pass the floor back to you, Vanessa. Thanks very much.
Great, thank you so much. Yeah, I think this is really, very, very interesting. And just from my side, before we sort of go into a few more questions, and I already see there are some questions from the audience, just two comments. First of all, on the cold spots. So for Early Warnings for All, we know we promote cell broadcast, so that are very, that are warnings sent over mobile networks. And there it's important, we only need 2G connectivity. So we have this, wide availability of networks. But of course, the analysis is also interesting for other services or applications, some of which may need more data. So, 3G, 4G, and so on services. So really, I think, interesting, not just for the Early Warning for All initiative and for early warning systems. But also what's I think interesting is where, we look at where people are, but sometimes people are not where they live. So the mapping is important also. When people, for example, work in a different place, they're in mountainous areas or they're, at sea. So it's important really to have these maps and understand that. And just one last point I wanted to make, and this is also because I used to work in the ITU statistics division, where we worked a lot with the national statistical agencies, and I remember we were always very eager to get the survey, household survey data. And the issue with that, of course, it it's only done because it's very costly. It's only done every few years. Also, it takes very long to analyze the data. So I think, it's really, really so amazing to have this population data, which is, I think so complementary to the household and the census data produced by countries, and so valuable, again, not just for the early warning connectivity map, but also, for so many other use cases. And we're really grateful for this partnership with Microsoft, and for this for the amazing data you provide, and also, of course, our other partners. Now, I already see there's a few questions from the audience, and maybe I'll turn to these first. The first question I see is from Ravinda Bala, and the question is, how good is AI in detecting thatch and mud buildings that are common in many rural communities, for example, in East Africa? And I think that question is for you, Caleb.
Yeah, so we do standard sort of machine learning evaluations where we hold out part of our labeled data and test on that. We've never stratified by like small single standalone buildings, but it's something that we do check visually. So I guess the short answer is that we're not sure. But one thing that we do have is a open visualizer for the dataset as of 2023 Q4. So if you have a place that you're interested in, you can check that out. And then if you're noticing kind of missing buildings, or it looks good to you, then definitely send us feedback.
So I guess it means you're also always sort of improving the model, right? And improving the data that you're producing.
Yeah, exactly. We retrain quite frequently, and then kind of try to adapt the model to correct errors that we find, and we find all different types.
Okay,
These
great.
global mapping efforts are really how do you balance finding all of the thing that you're looking for, which in this case are buildings, with making the model not produce too many false positives. So detecting things that aren't buildings as buildings.
Great. And I guess similar to also the connectivity data, where we also, always trying to improve, of course, the data and the data sources. There's another question from Michael Falkor. Hi there. Would you be able to tell us how EWCM can guide decisions between expanding mobile networks and using alternatives like radio, satellite, or community alerts? Paul, do you want to have a stab at that? And then maybe Cheryl, if you want to add anything.
Yeah, I'd say it's a good question, and there's not one size fits all. There's not just one solution that fits all. It's as you well point out, there's a combination between these connectivity cold spots don't include radio or television signals, and we know that there's satellite connectivity covers every square inch of the Earth. So this is focused on terrestrial broadband and fixed broadband and mobile networks. I just want to point out, like, an example for this is in Vanuatu, and we were doing some work in Vanuatu last year, and it's quite a interesting situation where it's exposed to, it's an archipelago with many islands. It's exposed to, it's a multi-hazard environment, so you can have one cyclone, then another one following, then an earthquake. So when these networks get taken out, there can be more people offline. And it was fascinating to hear a story about a community alert program amongst a women's association in Vanuatu who could spread the word. And they had a reach of like half the population of Vanuatu, because it's in everyone's interest to pass this news on. So absolutely, like a combination of different strategies depending on the exact situation on the ground. Sherelle, do you have any thoughts?
I think I agree with you, what you just said and what Vanessa said. You have to use all the tools available to you, not just to sell broadcast from telecommunications, but you also must have a great game plan on the ground by using radio. And for Liberia, it's very effective, the radio communication, and because we have some of these small community radio stations that go around. So you must make it a point to use all of the tools that you have available to you, particularly the cell broadcast, because there are some areas that people are so isolated. They might not be able to have those information by radio, and so giving them access to mobile phones where they can receive the cell broadcast information through cell broadcast or 2G will be very important. So that's all I can add.
And if I can just add one thing, once you have all of these layers, so the population layer, the connectivity layer, and the risk layer, you can actually simulate if you had to put down new cell towers to improve coverage, or if you had to increase the power of existing cell towers, where would the right places to put those be that maximize the new coverage? And that's one problem that we're working on under kind of a large amount of assumptions, and showing that there's kind of a wide variety of downstream use cases for when you have all these data layers organized.
Mm-hmm. Great. It's again for informed policy making and investment decisions too, right?
Exactly.
So yeah, great. Okay, excellent. Cheryl, just also, from the Liberia results, can you please just say where, what were sort of the most surprising or unexpected insights that the mapping tool revealed, particularly maybe those that were not previously visible through existing data, and, how, sort of what impact, what difference does it, do these results make to the Liberia Telecommunications Agency?
But I think from a presentation, it's evident what has happened. Like I said at the end, it's a different thing when you just have numbers, because what was happening in the beginning was you have an operator send you the number of the percent population percentage coverage. You have another operator send you their percentage coverage, but we never had a consolidated data to understand the entire national field of what's going on. And that's what the early warning for our system allows us to do. We could bring those data together and then have one set. So now we're seeing broadband 90 something, which was very surprising to us because we were still thinking that it would be like 70 something. And I think even Paul just said it. Actually, it was a joke. And it's funny because there are people in this country who still do not believe that data. They don't. So it's real and it's actually factual. It's made so much impact. I don't want to go over what I just said, but I think if the slides that are explanatory, Vanessa, I don't know, except maybe you want to be a little bit direct, maybe I can answer that question.
Great. Mm-hmm. So one question, Paul, also, and Caleb already mentioned how there's efforts to improve the AI data, but maybe can you say a little bit about more concretely what efforts you're making to improve the connectivity data? You mentioned the crowdsourced data that's feeding into the base layer, the DCM, but also more data sources. Are we looking at more data sources, the better the connectivity then is with these data sources, and how are you working with the private sector, and other specific efforts that are undertaken to expand on what we already have?
Yeah, so what I'd like to say is that with the connectivity data sets, we've been working with them for like 5 years, and we've built up a lot of experience of working with them and a lot of good baseline data. And we know that because this data is usually collected, it's crowdsourced, which means that it comes from 1, 2, 5% of users are sending the data. Instead, what we're doing, spending more time on at the moment, is using the field testing with the Android, the Speed Checker Android app. And so what we can do with that is we can be really targeted where we go. So if we think there are cold spots, then you can go there and test them with the app. And which is what the pilot in Liberia was doing during December. Now we've also been using this in emergency response situations. For example, in Jamaica after Hurricane Melissa in October last year, where there were different teams deployed to the ground who were setting up emergency telecom networks. And we were in touch with them and we were asking them to download the app and to be sending results back. Because at the same time, these teams were looking to understand where they should be going, to where there was demand and where networks were down. We've also been using this Speed Checker app to measure connectivity in refugee camps. And that was quite recent. We were doing that last year, and it's very fast. So we get the results back like within an hour into our database. And so in a real time, I mean, in a disaster context, we're using it to understand where networks have been damaged or they've gone out because of a cyclone or another disaster event. But it's also a very powerful tool to identify in non-emergency situations where these connectivity cold spots are. Yeah. So I could talk for a long time about it, but I'll stop there and that's the
Great.
thing. Yeah.
Great. Yeah, maybe another question, Caleb. So looking ahead, what future enhancements or changes or additional data sets do you think could further strengthen the early warning connectivity maps impact for countries like Liberia, and others, of course?
So I think two directions. One is the one that I was touching on in the last response, showing kind of the different downstream examples of the different downstream applications that you can now start to tackle once you've kind of consolidated all these layers. One being like where to expand out existing mobile networks. Another being where people are most at risk and like adding in different risk layers over things that we don't already quantify. The second main direction is just improving the base layers like we've been talking about. So for the building density side of things, that means adding more imagery, more precise training labels, better understanding of where the model is currently working well and where it's not working well. And then on the connectivity side, always improving the connectivity maps that we're using to kind of stitch everything together.
Great. Yeah, and we look forward, of course, to working with the different teams on these pieces. So we're coming to the end of the session. So first of all, really on behalf of ITU, I'd really like to thank all of you, and maybe just a few key takeaways from our session today. First of all, connectivity coverage alone is not sufficient. We must understand who is actually reachable when the hazards strike. So we've seen today the use of AI to map populations to connectivity, which is an excellent example of the use of AI to address gaps in early warning systems, and of course taking advantage of the huge amount of satellite data and information that we have access to, which is really creating a lot of I think new insights that we we weren't aware of and we weren't able to use before. So again, excellent use case of AI. Then the early warning connectivity map is really a practical and evidence-based tool to identify connectivity cold spots. So again, where are people at risk and without connectivity, where can we not reach them? And so again, this is really at the heart of the Early Warnings for All initiative to make sure that from the ITU perspective, we can ensure once something is happening and we need to send a warning that we are able to reach those people at risk. And I think most importantly, probably the early warning connectivity map is designed to support action. And from targeted investments, we mentioned those, but also to alternative communication solutions to stronger national early warning systems. So we talked about, we addressed the multi-channel approach. It's not just cell broadcast, it's also alternative communication channels that we really need to take advantage and use, especially in areas where we are not able to reach people that are at risk and outside of digital connectivity. So again, on behalf of ITU, I would like to thank our partners at the Microsoft AI for Good Lab, at Planet Labs and IHME, and also our colleagues from Liberia, especially you, Cheryl, for sharing the experience and your expertise. Thank you to everyone who's joined us today. We encourage you to explore the early warning connectivity map further and also to continue the conversation on how connectivity can truly help save lives. We will also be having a workshop at the AI for Good Summit in July with more details and more use cases on this topic. And of course, we hope to see you then. And thank you all and have a wonderful rest of the day. Thank you very much.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.